So now that we've added and subtracted vectors and kind of talked about what they are, we're going to talk in this video about multiplying them. Now, multiplying is a bit strange because, well, so you and I, we all know that if I did, say, 3 times 4, really easy, that's 12. But if I have two vectors, let's say we have u is the vector -3, 1, and v is the vector -2, -5. What does it mean to multiply these two vectors? -3, 1 times -2, -5. So this is kind of a weird thought because what do you multiply? Do you distribute? Do you add stuff? And so what mathematicians decided was there's actually two ways to multiply. We're going to talk about, today we'll talk about the dot product. This is sort of the most common way. The other one's called the cross product, and this doesn't really make sense until you get to three-dimensional work. So right now we're kind of stuck to our xy coordinate plane. But if we added a third coordinate, z, for example, then we can use the cross product. So we won't use this at all in this class, just something to be aware of when you get to, say, three-dimensional linear algebra or Calc 3. Not something that'll really get covered for a while. But this is what we'll be using throughout this section. So let's go ahead and define the dot product. If we have two vectors, let's call them just u1 and u2 are its components, and then another vector, I'll call it v1 and v2. Then the dot product, u times v, with this, make sure to always use that dot. That's why it's called the dot product. The cross product actually uses a little multiplication symbol like that. But u dot v would be this. And what we end up doing is we take the components and match them up. So u1 is going to go with v1, and u2 is going to go with v2. We're going to multiply those. So it's going to be u1 times v1 plus u2 times v2. So what's important to note here is this is now just a number. This is a number or a scalar quantity. It's not a vector anymore. So after we multiply these, or use the dot product on two vectors, we end up with a number. It is no longer a vector. So let's take a look at that example I just did before, the two vectors I put up in the beginning of this video. Let's take -3, 1 dotted with -2, -5. So what we're going to end up with is -3 times -2 plus 1 times -5. Multiplying that out is just 6 minus 5, so the answer would just be 1. Alternatively, we could use I hats and j hats, so a linear combination of those. So let's let w be the vector 3i hat minus 2j hat, and let's let t be the vector, let's just call it 3j hat. So now if you dot these vectors, notice first of all I've kind of left off a piece of t. If we were to write this out completely, we could say it's 0i hat plus 3j hat. And so in order to do this, we would just match up the components. So I hat goes with I hat. 3 times 0. I guess I should actually write down what the problem is that we're trying to solve. So 3 times 0 plus negative 2 times 3. And that would just give me negative 6 as my final answer. So overall, pretty straightforward. You just match up the components, multiply them, and then add your results together. The second one, I kind of try to make it a little bit more complicated, but that's just about as complicated as it can get. I try to be a little bit tricky by leaving out the I hat. You could always convert these into component form if you like that better as well. It's pretty quick to do, but not necessary. All right, so that is the dot product. Now, to kind of, I guess, pump this up just a little bit, let's take a look at an example combining a couple of different pieces. Part of this example that we're about to do relies on the definition of dot product that I mentioned above, where the dot product is a scalar quantity. It is no longer a vector. So we're going to let u be the vector we just saw above. Let's let it be negative 3, 1. We're going to have v is the vector negative 2, negative 5. And we'll also use w from above. I'll put it in component form just to match. So here are my 3 vectors, and I'm going to have you all calculate. We're going to do v dot w times u. Okay, so at first glance, this is a little bit strange because there's a dot in there for multiplication of vectors, and then there's regular multiplication of a scalar times a vector. So notice that this is the dot product, and that's going to give me a scalar quantity, and this is a vector. So at the end of the day, when I'm done with this problem, I am going to end up with a scalar times a vector, which if you look back in section 6.3, this is going to give me a vector. So your final answer should actually be a vector. Okay, so let's go ahead and start figuring this out. Let's determine a value for this dot product first. So we're going to take v times w. So that's going to be negative 2 times 3 plus negative 5 times negative 2. It's always good to write this step out because sometimes typos do occur when you try to do it all at once in the calculator. So I'd really appreciate it if you guys always write this first step out. But after this, if you want to just kind of do it in your head or on the calculator real quick, you can tell me what your final answer is. So it'd be negative 6 plus 10, so I'd end up with a positive 4. Okay, so let's go back to the original problem up here. I now know that v dot w times u is going to give me 4 times whatever u is. So let's go ahead and replace the u with its components. Distributing the 4, because that's how scalar multiplication works, we're going to end up with negative 12 comma 4. And so this would be my final answer. Or if you prefer I hats and j hats, you could say it's negative 12 I hat plus 4 j hat. And that is the dot product. So that's just kind of the definition and a couple of more straightforward examples. In the next videos, we're going to talk about a little bit more that we can do with the dot product.